Hi everybody, and welcome to my next video on spectroscopy, where we're going to look at using nuclear magnetic resonance spectroscopy to identify the number of carbon environments in an organic molecule. Now, before we get into that, I need to explain a little bit about how carbon NMR works. And please bear with me, I'm no way, shape or form an expert in carbon NMR. But if you want to find out huge amounts of detail, please check out some of the other videos on the internet. Alternately, you can listen to this, and I beg your indulgence for just a minute or two. So when you have some atoms that have an uneven number of particles in the nucleus, that's protons and neutrons, then they have a characteristic called magnetic spin. Now, atoms with this characteristic include hydrogen 1, so that's the main form of hydrogen. It includes carbon-13 and other more unusual isotopes such as nitrogen-15, oxygen-17, etc. So if you take these atoms, which occur naturally, as a known proportion of the naturally occurring atoms of that type, and you expose them to electromagnetic radiation, in this case in the form of radio waves, at a certain frequency, depending on how protected that atom is, its spin will flip in the opposite direction. So this nucleus acts like a teeny tiny magnet. And when we expose it to radiation of a particular frequency, it will make that spin change direction. And with the right equipment, we can detect that change in spin at the particular frequency that it occurs at. The frequency that it occurs at depends on what that atom is attached to. So how much the things that are attached to that atom remove the electrons away from it, so de-shield it, or allow the electrons to protect it. Ultimately, what it gives us is information about the carbon skeleton in a molecule. So it tells us how many unique carbon environments there are, and it tells us what things are bonded to those carbon atoms. Now, that phrase, unique carbon environments, is really important. It is probably one of the key concepts, and it's one of the things that people stuff up quite badly sometimes. So a unique carbon environment considers all of the groups that are attached to a carbon atom, not simply the atoms that are attached to an individual atom. So, you might have a carbon that's attached to 2 hydrogens and 2 carbons, but we don't think of those 2 carbons as 2 carbons. They might be 2 methyl groups, or a methyl group and an ethyl group, which is quite different, or 2 ethyl groups, which is different again, or a methyl group on one side and a carbonyl group on the other side, which is different again. So all of those things affect what is a unique carbon environment. Now, rather than me talking about this any further, I think it's best to actually see it. So, starting off with a nice simple molecule such as methanol here. In a methanol molecule, there is only one carbon atom. So there can be only one carbon environment, which you can see in the spectra. Here's the spectra for methanol. We have one single peak, which relates to one single carbon environment. Now, if you've only got one carbon, then figuring out how many carbon environments you've got seems pretty straightforward. It can get slightly more complicated. Here we have ethanol, and I hope you can see that when you look at the ethanol molecules, that the 2 different carbons in the ethanol molecule are in different carbon environments. One carbon is attached to 3 hydrogens and a methoxy group. The other is attached to a methyl group and a hydroxyl group. And so when we look at the spectra for that molecule, we see 2 distinct peaks because we have 2 different carbon environments. Where those peaks are in the spectrum tells us something about what those carbon atoms are attached to, but I'll talk about that later. But now we come to this molecule, which is propanone. Some of you might know it as acetone or nail polish remover. And if you have a look at this molecule, you can see that there is the two CH3 groups, one on either end, and both of them are actually attached to identical things. The carbons in those two CH3 groups, each of them is attached to 3 hydrogens, which is attached to a double bond oxygen, which is attached to a methyl group. Doesn't matter which way you look at it, both of those are attached to identical things. And so we actually only have 2 carbon environments in this particular molecule, even though we have 3 carbon atoms. We have 2 carbon environments, and so we have 2 peaks. And that's where things start to get kind of interesting with NMR spectroscopy, and carbon NMR spectroscopy particularly. So let's have a look at the next one. Here we have propanol. And propanol has 3 different carbon atoms. The first carbon, the one that's attached to the hydroxyl group, has 2 carbons and an ethyl group attached to it. The second carbon has 2 hydrogens, a methoxy group and a methyl group. And the third carbon has 3 hydrogens and an ethoxy group. So all 3 carbon atoms have different carbon environments. And so we see a spectra which has 3 distinctly different peaks. In contrast, if we look at propan 2-ol, as opposed to the previous spectra, which is propan 1-ol, hopefully you can start to see that the 2 carbons on each end, carbon 1 and carbon 3, are actually in identical carbon environments, and so this particular spectra has only 2 carbon environments, or this particular molecule has only 2 carbon environments, so it has a spectra with only 2 peaks. Now, let's have a think about how many carbon environments in each of these molecules. So if in doubt, I want you to actually pause this video and think about these things as we look at it. So first off, we have the molecule pentane. We have a CH3, a CH2, a CH2, a CH2, and a CH3. So how many carbon environments does this molecule have? Pause it, think about it, write down your answer, come back and have a look and see if you're right. Okay, so did you say that this molecule had 3 carbon environments? Or did you pick 2? The reason it has 3 carbon environments is that the CH2s at carbon 2 and carbon 4 are different from the CH3 group at carbon 3. Okay? This is kind of hard to explain without me scribbling all over things, but I'll do my best. So carbon 1 is a CH3 group, and that is exactly the same as carbon 5. So there's 1 carbon environment. Carbon 2 is a CH2 group, which is connected to a CH3 at one end and a propyl group at the other end. Carbon 4 is identical to that, whereas carbon 3 in the middle is a CH2 group attached to 2 different ethyl groups. So that's why it has 3 carbon environments. Okay, so now have a look at 2-methylbutane. Again, I suggest you pause this video for a second, think about that, decide how many carbon environments you think it might have. Okay, have you done that? Did you choose 4 carbon environments? If you did, give yourself a nice big pat on the back. Okay, it has 4 carbon environments because the 2 CH3 groups on the left-hand side are both attached to the same length of carbon chain, which is different to the CH3 at the other end. The CH3 at the far end, the one that's identified as number 4, is attached to a CH2 and then this branched chain group. The CH3s at the left-hand end, the ones identified as carbon 3, are both attached to a CH, which is then attached to everything else. So that makes them different. So Pentane, you would expect to see 3 peaks in the NMR spectrum. 2-methylbutane, you would expect to see 4 peaks. So immediately we can start to see some differentiation in the spectra between these two molecules. Okay, moving on, propan-1-ol. Here's the structure of it. Pause the video for a sec and think, how many carbon environments does it have? Did you choose 3 carbon environments? Well done. Yes, each of those carbon atoms is a different carbon environment. Now let's have a look at the last option today, propan-2-ol. Here's the structure of it. Pause the video, stop and think. How many carbon environments do I have? Okay, what did you come up with? Did you choose that there are 2 carbon environments? If so, give yourself a nice big pat on the back. That is great work. That's where I'm going to stop today's video. The next one I'm going to look at will be considering how many or how we can identify what the carbon atoms in those different carbon environments are bonded to. I'll see you for the next video. Thanks, guys.